Hello. So today we are going to talk about work and energy. So the first thing we want to talk about is energy. So energy is actually the physics of pain. So what that means is if something is going to be more painful, that means it has more energy. So let's first talk about work. So work is sort of the foundation of energy. So scientific definition of work is the ability to cause motion. Okay? So it's anything that can cause something to move. So an example would be pushing a box. Okay, so if I'm pushing a box, I'm causing that box to move. Okay? So there are two parts of this. So W, work, is F times D times cosine theta. So let's look at this. Let's say I have a box. I'm applying a force. Okay, so I want to find out how much work I'm actually doing. Well, I need to figure out how far I actually push this box. So that's my distance. Okay, so I have my force times my distance. That gives me work. And then there's also this cosine theta part. So that part is really just asking, is my push actually helping it move, or is it unrelated? So for example, if I'm pushing this way, and then the box moves this way, did I help it move? No, I didn't really help it move. So my force, this force here, doesn't count. Okay, so the way we figure this out is by looking at the angle between the force and the distance. Okay, so if the angle is the same, so in this example, my distance is to the right, and the force is also directly to the right, well, cosine of 0 is just 1. Okay, so oftentimes you don't really need to worry about the cosine theta. So if they're both in the same direction, you don't need to worry about it. If they're in opposite directions, it's just a negative sign here. Okay? Now, if I have something like this, let's say 30 degrees, well, now I need to actually worry about it. So then I would just do F times D times cosine 30. Okay? So remember, your force needs to actually be contributing to the motion. So that's a really important thing. Okay, so let's continue. So, why is no work done by a student who is carrying a bucket of water? So another example of this very similar idea is if I have this marker in my hand and I'm moving my hand side to side. Okay, which direction is the force of my hand? Yeah, that's right. The force of my hand is straight up. So here's my marker. Okay, so the force I'm applying is straight up. I'll label that as F. Okay, but the question is, which direction is the marker moving? Yeah, the marker is moving either this way or this way. Okay, so if you notice, the angle here is 90 degrees. Okay. And what is the cosine of 90 degrees? Well, that equals 0. Okay, so in both of these cases, my force, what I'm pushing, doesn't actually contribute to the motion. What's the force that actually keeps it in my hand? What's the force that keeps it from sliding? Right, that would be friction. So friction is actually doing the work, whereas I am not doing the work. Because my force is straight up, while it's moving side to side. Okay, so once again we have work equals force times distance times cosine theta. Now this is a new set of units. So work, W stands for work, and it's measured in joules, which is normally just written as J. Okay, so work stands for that. Just a quick review, F is force in newtons, D is distance in meters. Okay, so let's look at our first example problem. How much work is done on a vacuum cleaner pulled 3 meters by a force of 15 newtons at an angle of 30 degrees above the horizontal? So let's write down our variables. Our F equals 50. Okay, our distance equals 3 meters, and then our angle is 30 degrees. So let's go ahead and write our formula first. So work equals force times distance times cosine theta. So work equals force, which is 50 times 3 times cosine 30. So that should give us something around 75. I'm just guessing. You can go ahead and punch it into a calculator and find out what that is. Okay, let's move on to the next part. Okay, so we have a 20 kg suitcase is raised 3 meters above a platform by a conveyor belt. How much work is done on the suitcase? So in this case, we're only concerned about going up, okay? So if I'm only concerned about going up, let's draw a little free body diagram here. Okay, what are the two forces acting on this force as it's being moved up? Well, we have a downward force. What's the downward force? Yes. So the downward force is mg, and we're going to assume that it's a constant velocity, okay? There obviously needs to be a bit of an acceleration to get it moving, and then there'll be a deceleration at the top, but overall it's pretty close to a constant velocity. Okay? So what force must be pushing it up? Well, we could label this Fn, or we could label it Fa as like the applied force. And then because we know that this is a constant velocity, what do I know about these two forces? Yes. Remember, constant velocity means acceleration is equal to 0. If acceleration is equal to 0, F net equals 0, which means these two forces must be equal. So we have I'll just call it Fa equals mg. Okay, so let's go ahead and let's define our variables. What is m? M is 20. Okay, what is d? D is 3 meters. Okay, so let's go ahead, and our work is equal to F times D times cosine theta. So the work is equal to 20 times 10, so that's my mg here. I'll actually write that out. mg d cosine theta. So this part I don't need, because I'm only looking at the part that's in the y direction. So I can actually explain that a little bit better. Let's say I have this inclined plane here, okay? So I'm be pulling up like this. I'll also be having a force that's up like this. But the nice thing about the way work works is that I'm really only concerned about this direction, the y direction, okay? And I know that overall I must have a force like this. Otherwise, it can't move up, right? So because of that, I don't really need to worry about all these angles. I just need to worry about how much does it move up, okay? So I don't need to worry about this cosine, so I just get work equals 20 times 10 times 3, so that would be 600 joules, okay? So, 600 joules. So that was the end of that first part, and I will see you for the second part in a few seconds.